Hey everyone, and welcome to This Explainer. Today, we're diving into the totally fascinating world of polymer extrusion. We're going to unpack exactly how raw, seemingly basic plastics are transformed into the highly specialized essential products we rely on every single day. If you've ever wondered how they make everything from the super thin plastic wrap in your kitchen to the ultra strong composite rebar replacing steel in construction, well, you are in the exact right place. So here's our game plan for today. We'll start with a quick overview of extrusion technology, then get into the basic properties of plastics. After that, we'll cover polymer chain orientation, look at how to optimize those processing parameters, and wrap up with some incredibly diverse real-world applications. All right, Section 1, Overview of Extrusion Technology. Let's get right into it and see how this actually works on the factory floor. At its core, extrusion is a continuous manufacturing process. Think about injection molding for a second. That's making one discrete part at a time, right? Well, extrusion is the exact opposite. We heat raw thermoplastics, or rubbers, past their glass transition and melting points until they become this gooey, viscous liquid. And because the process just keeps going, we can create products of literally unlimited length. We're talking endless rolls of film, miles of piping, you name it. Here's how the whole process actually comes together. You start by feeding raw plastic pellets into a hopper. They drop down into a heated barrel where this massive rotating screw shears and pushes the material forward. The heat melts it down, but the real magic happens at the die. It's essentially a shaping tool at the very end of the extruder. The molten plastic gets forced through, takes its new shape, and boom, it hits a water tank to cool and solidify right away. Finally, a pull roller keeps the tension perfectly dialed in before the continuous product is cut to size or wound up. Now, the absolute key thing to grasp here is the flow. It has to be perfectly continuous. Because the molten plastic glides through a highly polished die without any stops or blockages, you get products with incredibly high surface gloss. If that flow breaks or pauses, the material actually degrades. It's a delicate operation, but when it works, it forms the manufacturing backbone for everything from standard cable coatings to building trims. Moving on to Section 2, Basic Properties of Plastics. To really master extrusion, we absolutely need to know our raw materials, their properties, and how they behave. When we look at common polymers, things like high-density P, low-density P, and polypropylene, the numbers tell a fascinating story. Take polypropylene, or PP. It boasts a melting temperature of up to 170 degrees Celsius and a massive elastic modulus of 1,400 megapascals. What does that mean for our extruder? Well, you're going to need higher heat to get it flowing, but the payoff is huge. The final product becomes incredibly robust and heat-resistant. On the flip side, something softer like low-density P has an elastic modulus of just 200, so it behaves completely differently both inside the machine and out in the real world. It all boils down to an engineering trade-off. When you're picking a base polymer, you have to choose wisely based on what you're making. High-density PE is your go-to for high stiffness, high yield stress, and better heat resistance. It is seriously tough stuff. But low-density PE is highly prized for its flexibility and lower melting point. It's actually a lot easier and way more energy efficient to process if you don't need all that intense structural strength. To put that high-density strength into perspective, just think about a standard plastic grocery bag. Thanks to the inherent properties of high-density PE, a bag that is a mind-bogglingly thin 0.05 millimeters thick can hold up to 10 kilograms of groceries. I mean, it just doesn't tear. That is an absolutely insane strength-to-weight ratio for something we use every single day. Which brings us perfectly to Section 3, Polymer Chain Orientation. Because how exactly do we get that kind of strength from such unbelievably thin plastics? Let's look at bi-oriented polypropylene film, or BOPP. The secret to its toughness isn't just the PP material itself. It's what we do to it after it leaves the die. During the pulling stage, while the plastic is still at this very specific, carefully controlled temperature, we deliberately stretch and align its polymer chains. It's basically molecular physical therapy designed to drastically boost its properties. By stretching those polymer chains in two directions, longitudinally as it's pulled forward, and transversely, or side to side, manufacturers create this tightly linked crisscross molecular grid. Because the molecules are permanently locked into this organized structure, the material's resistance to tearing goes through the roof. That's why you can't just easily rip a high-quality packaging film right down the middle. All right, on to Section 4, Optimizing Processing Parameters. Pulling off that molecular alignment requires some serious, strict control over the machinery. This is especially true when we get into advanced composite materials, like glass fiber reinforced polymers using epoxy resins. Getting maximum tensile strength isn't just about melting plastic anymore. It is a three-way balancing act. You have to absolutely nail the curing agent ratio in your epoxy, the exact pulling speed through the machine, and the precise temperature in the curing chamber. Every single one has to be spot on. If those parameters are off, it's a disaster. Pull the fibers too fast, and sure, productivity goes up, but only the surface cures, leaving the inside weak and practically useless. Crank the heat too high, you will literally burn the epoxy. And if it's too cold, the composite never fully solidifies, and the whole structural bar just comes off the line completely soft. But when you get the speed, heat, and chemistry perfectly balanced, the results are a total game changer. An optimized polymer composite can be up to 5 times lighter than traditional steel, all while packing 1.5 to 2 times the tensile strength. This level of optimized extrusion is literally paving the way for the next generation of infrastructure. And that brings us to our final stop, Section 5, Diverse Real-World Applications. Let's see how mastering these plastics shapes the products all around us. The sheer range of what we can do with these common extrusion plastics is just astounding. On one hand, we have heavy-duty industrial fishing ropes. We extrude these with highly oriented polymer chains strictly along the longitudinal axis, prioritizing maximum pulling strength so they don't snap under tension. And right next to that, using very similar polymer bases but engineered for high impact resistance, we mold rigid, hard-shell consumer luggage that actually survives the modern airport baggage claim. It all comes back to understanding those base properties, because polypropylene has that high melting temperature we talked about earlier. We extrude it into food storage containers that won't warp in your microwave or dishwasher. But the exact same core scientific principles of thermal and chemical resistance also allow us to create highly precise, sterile, life-saving medical syringes. It translates across totally different industries. Even the cars we drive are full of extruded and molded polymers. The dashboard, the steering wheel casing, the air vents, automakers rely heavily on these advanced plastics. Why? Because by utilizing them, engineers can drastically reduce the overall weight of the vehicle, which boosts fuel efficiency, while still giving us beautiful surface finishes and incredibly precise shapes. So, from a simple hopper full of plastic pellets, all the way to the high-tech interior of your car, the journey of polymers is pretty incredible. And as we keep pushing the envelope with faster pulling speeds, tighter temperature controls, and wild new molecular engineering, you really have to wonder, what kind of ultra-strong, sustainable supermaterials is this technology going to allow us to build next? Thank you so much for joining me on this explainer. Keep exploring and keep questioning the science that builds our world.